Okay, good day, grade 11s. I hope you are doing well. We are going to have a look at a couple of past paper questions. And we are going to start off today by having a look at the topic of resultants. So we're going to have a look at, we're going to start by having a look at a 2018 paper. This is question 2, it's out of 10 marks, and it all has to do with resultants and vectors. So the question says, two forces of magnitude 50 newtons and 80 newtons act at a point on the Cartesian plane in the directions shown in the sketch below. So we can see that we have an 80 Newton force acting to the right. We also have a 50 Newton force acting north of west at 30 degrees. So to start off, question 2.1 says, give the correct term for the following description. A single vector having the same effect as two or more vectors together for 1 mark. That would be a resultant. The next question says, calculate the magnitude of the vertical component of the 50 Newton force. So this is quite nice because they've kind of broken it up for us. But generally we're going to be doing the same thing in these types of questions, which is breaking up all the forces that act as angles into their horizontal and vertical components. We're then going to be adding and subtracting them. We can only add and subtract collinear forces, so we want to get them all vertical and all horizontal before we can add and subtract them. And then what we'll do is we'll find the resultant of all of the forces acting at that point. So let's dive straight into it. Basically what's happening here is we have an 80 Newton force acting this way. Okay, and we have a 50 Newton force acting in this direction, and that is at 30 degrees. Okay, what we're going to want to do is we are going to want to take this 50 Newton force and resolve it into its two component vectors. We can call this force F, in which case we'll call this one Fy, which is the vertical component, and we can call this one Fx, which is the horizontal component. Now, how do we figure those out? Well, a very nice trick to do over here, if it helps you with trigonometry, is to simply bring this force over and create a closed triangle. So again, how that would look is we would have our Fy, we have our Fx acting in this direction, and our hypotenuse of our right angle triangle is always going to be the force itself, which in this case, again, is 50 newtons. So let's ask ourselves quickly, what is Fy? Because the first question does say that they want us to calculate the vertical component, which is our upward component in this case. Fy is going to be equal to, well, that is an opposite, and our force itself is our hypotenuse. So that opposite over hypotenuse gives us F sine of theta. Okay, we can calculate that very quickly. We know that F is 50 newtons, sine of 30 degrees. So if you plug that into your calculator, you will find it to be exactly 25 newtons. So that is the answer to the first question, 2.2.1. They now want you to calculate the magnitude of the resultant force, and then after that, the direction of the resultant force. Again, we're always doing the same thing here. So what I'm quickly going to do is I'm going to go and figure out what our horizontal component is in this case. So we can write Fx is equal to, now again, we can see that this is an adjacent and this is a hypotenuse. So that is going to be f cos of theta. So we find that fx is equal to 50 cos of 30 degrees. And therefore, the horizontal component is going to be equal to exactly 43,3 newtons. All right. There we have it. So we've got these two components now. And let's quickly analyze again what's happening in our situation, okay? So if I look solely at our horizontal components, what are we dealing with? Well, we've got this force of 80 newtons, 80 newtons acting to the right, okay? And Fx is acting this way to the left. So again, that is 43,3 newtons, okay? So if I wanted to resolve just the horizontal forces acting on this point, I would write something like Rx is going to be equal to, now I'm going to choose quickly the right direction as my positive direction, okay? And generally what we do is we like to take up as our positive direction when working with these. You can do the opposite if you want. Sometimes in physics it helps to make down positive, but generally we like to take to the right as being positive and going up as being positive. So that means that we have 80 newtons minus 43,3 newtons, okay? So we therefore find that Rx is going to be equal to 36,7 newtons, okay? And notice that this is a positive value, okay, which basically means it is acting to the right, okay? If we have to resolve our vertical components now, we'll find that we only have one force that's acting upwards, and that is the Fy over here, okay? That is a vertical component of our main force, or our 50 Newton force, shall I say. So basically on this point here, we only have one force acting upwards, and that's Fy, which is 25 newtons. Okay, so to resolve that, we can just say, you know, Ry is equal to, well, 25 newtons. Okay, and it's acting upwards because it's positive. So you can say, you know, acting upwards. Okay, so why do I call it Rx and Ry? Well, again, we're trying to find the resultant force. So these are the resultant components of our final force, if you want to think of it that way. We said that Ry is acting upwards. We said that Rx is acting to the right. And so we expect our resultant force R to be acting somewhere in this direction. We also have an unknown angle of theta. So we are going to now resolve the magnitude of this resultant force and the direction of this resultant force. So what does that look like? Well, a very common thing to do is to form yourself a little triangle like this. Now, I know it looks like a closed triangle at the moment. This is a resultant force, which means that the object is going to be moving. And when I say moving, I mean accelerating. But I like to just draw a little triangle like this because sometimes it helps me to figure out my trigonometric ratios when dealing with this angle later. So you are more than welcome to do that if you want. All right. But what we're going to do now to solve this problem is we are going to use Pythagoras, which is r squared is equal to Rx squared plus Ry squared. All right, I'm going to square root both sides, and what we end up with is our theorem that looks like that. And now I'm just going to plug in the values of Rx and Ry. We said that Rx was 36,7 newtons. Don't forget to square it. And Ry is 25 newtons. Don't forget to square it. And we'll find that our resultant force is equal to 44,41 newtons. Okay. Now, we can't specify exactly which direction it is moving in because we haven't figured out what theta is. So for the next question over here, we want to know the exact direction of the force, and then we can describe it completely. So what we're going to do is we're going to use trigonometry to do that. Again, you can make yourself a little triangle like this if it helps you. Okay, I'm going to use Ry and Rx to solve this problem. That is the opposite and the adjacent sides. And if you know your trigonometry, you know that tan of theta is equal to the opposite over adjacent. Okay, in this case, our opposite is Ry and our adjacent is Rx. Okay, so you can go and plug those values in, or you can immediately use the inverse function, Ry over Rx, and then we can plug in our values. So Ry we said was 25 and Rx was 36,7. So what we find is that theta is equal to exactly 55,74 degrees. All right, so what does this mean? This means that the resulting force, or resultant force, is 44,41 newtons acting at 55,74 degrees. And now if you want to know the direction or describe the direction of the resultant, we said it was moving somewhat this direction. Okay, we do have the x-axis over here and the y-axis over here. What you can also do is think of this as being north. You can think of this as being east. And with that in mind, it is acting north, right? It's acting northwards because our resultant is coming from the east going north. So it's acting north of east. So that I find is the easiest way to describe that. It's acting north of east. Okay. And there you have it. We have solved our first problem. Okay, let's have a look at our second problem now. This is question 2 from a November 2023 paper. And the difference between this one and the previous one is that we have a crate that weighs 15 kgs, which means that maybe we'll have to calculate some weight or some acceleration or something along those lines. And we also see that there are 3 vectors acting on this crate instead of 2, like the previous question. So the first question says, define the term resultant vector. Now the resultant vector is basically just the sum of 2 or more vectors. Just make sure that you're using the right definition from your government guidelines. But over here it says a single vector having the same effect as 2 or more vectors that are combined, or is the vector sum of 2 or more vectors. Now we want to calculate the resultant of these 3 forces, and the next question will ask us to explain why the 3 forces will not form a closed vector diagram. Okay, so let us begin. So we have a crate. Now again, I'm drawing a free body diagram. I recommend always drawing your own free body diagram, even if they don't ask you to do so, because it helps you to understand the situation better and break all these forces up into their component vectors, and it allows you to visualize them better so that you can add and subtract the vertical and horizontal components effectively. Okay, so our first force is F1, it's 500 newtons. We have F2, which is 600 newtons, and we have F3 over here, which is 450 newtons. Okay, here we have our y-axis, okay, and that F1 is acting at 30 degrees from the y-axis. We also have our x-axis over here. Let me just extend that, and this one is acting at 50 degrees from the x-axis. So that's going to play an important role in choosing which trig function to use when you are breaking these forces up into their vertical and horizontal components. So I'm going to go ahead and just make F1 a green color. Okay, and basically what I want to do here is I want to break this one up into its horizontal component, which I'll call F1x, and then I'm going to want to go and break that same force up into its vertical component, which I'll call F1y. So just for reference, I'll draw it over here like this. This is F1x, F1y, and again our force F1 is acting in this direction. Now we know that our 30 degrees is over here. All right, so I'm actually going to choose in this case to move my F1 horizontal component, F1x, up so that I have my triangle like this, and my 30 degrees is sitting right here in the corner. Okay, so I can quickly describe F1x as being the opposite of the 30 degrees, and we have the hypotenuse, which is always going to be the force itself. Opposite of hypotenuse is going to give you sine, so we have F sine of theta. In this case, I'm just going to go ahead and write 30 degrees there. We can solve this if we want quickly, or we can leave it in its current form and substitute it later. It's completely up to you. Let's quickly see if we have an answer for this. This is 500 sine 30, which is 250 newtons to the right. Just for reference, I do have the memo open on the side here, so I can quickly grab the answers and I don't have to use my calculator, but this is all for explanation to help guide you through this memo. Okay, so I can also go ahead and quickly just describe my vertical component for the same force of that 500 Newton force, and that is going to be F cos of 30. You know that if the one is sine, the other one is cos, but just be very careful when working this out. Make sure that you use the correct one to begin with, because if you accidentally write this as cos, it is going to stuff up all the calculations for you moving forward. And the scary thing about a question like this is that it's worth 9 marks. So if you accidentally wrote cos here instead of sine, as you know, in physics, we do not mark with CA marks like we do in mathematics. Okay? What that means is that if you make a mistake here, you are likely going to lose a lot of those 9 marks. So please be very careful about that. So I'm going to substitute this in here. All right, I always like to, wherever I can in physics, write your formula, substitution, and answer to try and attain full marks. So they say here that 500 cos 30 is 433,01 newtons. Okay. Another just a quick note is that for any of these calculations that you're doing and you end up with decimal places, like I would go and save that in my calculator as A, I would go and save that in my calculator as B, just so that when I am recalling these numbers or substituting them in formulas later down the line, that I am in fact using the number with the full decimal string. Okay, so there we have it. We've broken that force up into its x and y components. Let's quickly deal with F2 over here, and I'm just going to make it blue. So if I break this force up into its horizontal component, we are going to be left with F2x. That's what we like to call it. It's F2, but it is the x component, the horizontal component, and this one we'll call F2y. Now I'll do the same thing as before. Okay, I'll just name this F2x. This one's acting downwards. We'll call this F2y, and again our force F2 is acting somewhere in that direction. So let's identify where our angle is. Okay, and it's acting from the x axis. So I am in this case going to bring over my vertical component to try and form a little closed triangle. Again, this is just me sketching, okay? You don't get marks for this, but it just helps me to see which trig function I should be using, okay? So let's quickly describe what F2x looks like, and that is going to be F. Let's quickly double check this. We have our adjacent, and our force is the hypotenuse. So in this case, we have F cos of, sorry, not 30, 50 degrees. Okay, notice before the x component was sine, but now the x component of this one is cos. Okay, which means that it depends where this angle is. It would be a different story if they gave us this angle here. Okay, but we actually know that this angle is going to be 40 degrees because this is a 90-degree angle over here. So you could use that 40 degrees, but you would use sine instead of cos in that situation. Okay, but let us continue. We know that the magnitude of this force is 600 cos 50, and therefore F to x 600 cos 50 is 385,37 newtons. Okay, that is obviously acting to the right. Right, so you can write, you know, to the right. This one was up. Okay, and again, what I'm going to do is I'm going to save this decimal string in C. Okay, so again, what I'm doing is I'm saving these numbers for later use. All right, last but not least, let's get our vertical components here. What we have is this opposite over hypotenuse. All right, so that is going to be F sine of 50 degrees. So F2y gives us 600 sine 50. So F2y is equal to 59,62. Okay. 600 sine 50. Oh, there it is. Okay. So for Fy2 equals 600 sine 50, we get 459,63 newtons. Okay. Which direction is that acting in? It is acting downwards. Okay, I'm just going to save that in D on my calculator. And we say it's acting downwards, which means that if we take up as our positive direction, then that is going to become negative when we are dealing with it in just a second. Okay, so what does all this mean now? This means that if I need to find the resultant of the horizontal forces, I am firstly going to have this F3 of 450 newtons acting to the right. So I have F3, which is 450 newtons. Okay, on this point over here, which I'll just enlarge a bit, we have another force acting, oh no, we don't, not acting to the left. We have two forces acting to the right. Okay, we have two forces acting to the right, namely F2x and F1x. Okay, so we have F2x, which is 385.37 newtons, and we have F1x, which is 250 newtons. Okay, again, I'm going to take right as my positive. Okay, so if I need to find the resultant along the x-axis or along the horizontal axis, what am I going to have? Well, I'm going to have 250 newtons. This is positive. This one is also positive. So we're going to say plus 385.37 newtons. And this one here is going to be negative because it's acting to the left. So I'm going to say minus 450 newtons. Okay, we will plug that all into our calculator. And we will find that it is equal to 185.37 newtons. That is a positive value, so it is acting to the right. Okay, let's quickly resolve our y components. Okay, looking at the original plot here, we don't have any forces that are already acting upwards or downwards. We only have the two components, one of which is acting down and the other is acting up. Now I'm going to choose, again, I'm just going to choose up as being positive. And maybe I could even draw you a quick free body diagram that has those two forces here. So one of them is acting upwards, that is F1y, which is 433.01 newtons, and the other one is acting down, F2y, which is equal to 459.63 newtons. Okay, so in this case, we're going to have 433.01 minus 459.63. So my Ry value comes out to be a negative value here, and that value is going to be negative 26.61 newtons. And again, because it's negative, it means that it's acting downwards. Okay, so what do we have? We have this Rx, which is acting to the right, and we have this Ry, okay, which is acting downwards. Okay, and now we want to find the resultant of those two forces. So let me just make some space here. So basically what that looks like is we have this downward force, that is our Ry, and we have another force which is acting to the right, which is our Rx, and our resultant, as we would expect, is going to be acting somewhere in this direction. Okay, I'm going to go ahead and put my theta over here. I generally like to use my theta coming from the x-axis, although it shouldn't really matter too much. But let's go ahead and start by trying to find the magnitude of this. Okay, so because I chose to put my theta there, what I'm going to do is I'm actually going to shift this up. So we kind of have a triangle. Now this is not a closed triangle. The system is not in equilibrium. Okay, this object is definitely going to be moving, And when I say moving, it's going to be accelerating. And the reason for that is there is a net force acting on this object. And this object is a 15 kg crate. Okay, so we could go ahead and calculate the acceleration of this crate if we wanted to. Okay, but we're not going to do that in this question. What we are going to do is we are going to use Pythagoras to figure out what this resultant force is. So how do we do that? Well, we have r squared equals rx squared plus ry squared. Okay, I'm going to square root both sides and write my Pythagorean theorem like that. All right, and what we find is 5,37, and don't forget to square it, please. And our ry is 26,61. I mean, you can put the negative sign here if you really want to. Whenever we square a negative number, it's going to become positive, so it doesn't really matter. And we find that our resultant force is equal to 187,27 newtons. All right, to find the direction, I'm going to use Rx, and I'm also going to use Ry. The reason I want to use that is because I have those numbers hopefully saved in my calculator already. So tan of theta is equal to the opposite over the adjacent. Okay, what does that mean? It means Ry over Rx. Okay, then we can take the inverse trig function, and we find that theta, let's plug it in to make sure we're getting full marks for formula substitution and answer. So Ry we're going to take as 26,61 divided by 185,37. Okay, and what I find for theta, I'm going to do this on my calculator because I've done it a slightly different way to the memo. I have no idea how to use trig functions on this calculator. It doesn't seem to be working, but I'm going to assume that the answer is going to come out to be 8,17 degrees. Should be the correct answer for that. I see that the memos just used the other angle. What happened is the memos used this angle. So I'm just going to assume that this is the correct answer here. You can correct me if I'm wrong. I'm just struggling to do my inverse tan function here on my calculator. Okay, so what does this mean? Well, this means that the resultant force, the resultant force is 187,27 newtons acting at 8,17 degrees, okay? And now our resultant, just for reference, when we just calculated, is acting in this direction, so it's going southward from east, south of east. And that is our final answer. Okay, and then 2.3 quickly says, explain why the three forces will not form a closed vector diagram, and it won't form a closed vector diagram because closed vector diagrams only form when we have a system in equilibrium. In this case, we have a resultant force acting on the crate, which means that that crate is going to be accelerating in some direction. And because of that, we can't draw a closed vector diagram. The system is not in equilibrium, okay? There is a net force acting on the crate. In the memo, it says the resultant force is not equal to 0. Okay, let's do one last example for today. This is question 2 from the November 2022 paper. And I thought it would be nice to show you guys another version of this question where they're actually doing more of an application as opposed to just giving you a Cartesian plane. So the question says, a pulley system is used to keep a heavy object at rest as shown on the diagram below. Now, very important here, just from the text already, they said that the object is at rest. Now, when an object is at rest, we know that the F net, the net force, is going to be equal to 0. Okay, so if we do draw any closed vector diagrams, or if we draw a vector diagram, it is going to form a closed triangle, because I can tell you now that there are 3 forces acting on this object. So again, define the term resultant vector. As said before, it is basically the sum of all the vector forces. Please just make sure you study your definitions correctly so that you can get 2 marks for that question. Question 2.2 says, draw a vector diagram showing the forces acting on the object. Label the forces and indicate the angles on your diagram. So we're going to draw a vector diagram. It doesn't say to scale, although if you wanted to, you could. Well, it looks like these are quite big forces, so I wouldn't use a 1-to-1 ratio. You're not going to have enough space on your page. But you could go and draw a scaled vector diagram and then measure that resultant to see if your calculation comes out correctly. That is sometimes helpful. But before I even draw my vector diagram, I am going to draw a free body diagram. Okay, I always recommend that you draw a free body diagram to start off with. Okay, so first of all, our heavy object has some force acting in this direction, and that is this force acting around this pulley. We also have another force acting this way, which is this force acting down this pulley, and of course we have some heavy object which always has some component of weight, some weight acting downwards. So we have our weight acting downwards, we have some force, which, I mean, we could just call it force A and force B, acting this direction, which is 1,284.95 newtons. Okay, and we have another force acting this way, which is 1,440 newtons. Right, be careful here, because we need to take into consideration the angles at which these forces are acting. And this one is 40 degrees. Okay, coming from the y-axis, 40 degrees. And this one is 55 degrees coming from our x-axis. All right, so please just be aware of that. This, guys, is a free body diagram. Okay? This is not a vector diagram. Okay, a vector diagram would look something like this. So we have our weight acting downwards. Okay, then we have this force acting this direction. I'm just gonna call this one FB and call this one that's acting in this direction over here, I'm just gonna call this one FA for argument's sake. Okay. So there we have our 3 vectors. Again, they are forming a closed vector diagram because our system is at rest. Okay, and I'm just going to put the values in here to make sure that we're getting full marks. 12,084,95 newtons. And there we have it. The last thing we need to do is just to ensure that we are putting in our angles. Okay, I see that the question is out of 4 marks, so we can put our angles in. This one over here, as you can see, correlates with this part of our triangle over here. So we know that this angle is going to be 40 degrees. Okay. And then we have this 55 degrees. Now this one may look a little bit weird. 55 degrees is kind of coming off here. Okay. What that basically means is that we can go and try to calculate this full angle over here, or we can also try to calculate this full angle over here. We could try to use some Euclidean geometry to try and maybe solve this angle over here. How would we do that? Well, we have our weight acting downwards. This line over here, I don't know if that makes sense to you guys. But this line over here is acting at how many degrees would that be? Let's quickly see if we can do this in a nice effective way. Well, this would be 40 degrees. Okay, that's what we call vertical opposite angles. This would also be a vertical opposite angle here, which would be 55 degrees. If that's 90 degrees there, this would be, of course, 35 degrees acting that way. Then that one would be 35 degrees acting that way, because 55 degrees plus 35 degrees gives us 90 degrees. And if we must know if this is 40 degrees, then this must also be 50 degrees. Okay, so I don't know if that makes full sense to you guys. I hope it does. But basically this angle over here is 35 degrees. So we have 35 degrees there, 40 degrees over there. If we add these two together, we know that we'll get 75 degrees, and in a triangle we have 180 degrees. So 180 degrees minus 75 would give us 115 degrees. So we only really have to put two angles here, but you could also just imagine that that is 115 degrees. Okay, so it's not a 90 degree angle. Okay, I hope that makes sense. I'm sure there's an easier way to do that, but that's the way I just decided to do it there. All right, so let's move on. That is our vector diagram over there. It is labeled and we've indicated the angles on my diagram. So I'm just going to go put in all the angles there. We now need to calculate the weight of the object. Okay. The way I like to do this is I will break this vector up into its component vectors. So again, I called this one FB, so I'm just going to call it FBY. All right, that is opposing the weight that's going down. And I can also break this one up into its Y component. Now I called this one FA, so I'm just going to call it FAY. So basically what I have here now is my weight going downward, which is the force that I'm trying to calculate. And I have two weights acting upwards. Okay, namely FBY and FAY. Okay, what does that mean? That means that because the system is at rest, okay, because the system is at rest, the sum of my forces, okay, the net force, in this case acting in the y direction, okay, is going to equal 0. It is going to equal 0. And what is my net force? It is the sum of all those forces acting on the y-axis, okay, which is going to be my FAY. Again, bear in mind that everything acting upward is positive, everything acting downward is negative. I'm taking up as my positive direction here. Okay, so that's going to be plus FBY minus W is equal to 0. Okay, so this is the equation I've formulated for my situation now. Okay, let's quickly think to ourselves, what is FAY? Let's just do it on the side here quickly so we can see exactly what this is. FAY, sorry, I made it red. So let's just stick with the theme. FAY, which was my red force here, is going to be equal to what? Okay, if this is 55 degrees, what must this be? That is going to be 35 degrees, right? Because this is a 90-degree angle. So I can use this 35 degrees. Okay, this is my hypotenuse, and this is my adjacent. So we know that we're going to use cos for this. This is F cos of 35 degrees. Another thing that would work is if I brought this Fy over to this side and I used my 55, in which case we'd use sine to solve that, but we'd use sine of 55 degrees. So there's two ways. You could use this, or you could use F sine 55 degrees if you didn't want to go and work out that angle on the 90. Okay, nonetheless, I'm quickly going to plug this in. That's 1,440 cos of 35 degrees. Okay, and we can work that value out and save it in our calculator. Sure, you can go and work that out, save it in your calculator, or you could just keep it like this, because we can take this right here and we could very easily plug it into our equation there. Okay, so just to save time, I am now going to go and calculate this one. This is my hypotenuse from the 40-degree angle and my adjacent, so it's another cos. So I'm going to have FBY, which is equal to F cos 40 degrees now. Okay, and therefore my FBY is equal to what? 1284,95 cos 40 degrees. Again, if you wanted to, you could go and calculate that. Just remember to save it in your calculator so you have the full value. So we would save this one in A, we would save this one in B if you go and calculate that. But I'm going to show you a method where we can simply plug these values in here. So because we used red for FAY, I'm just going to do it so you can see it here. This is going to be 1440 cos 35 plus FBY, which is 1284,95 cos 40. Okay, and then what I'm going to do is, because this is a negative W, okay, I'm going to bring it over to the other side of my equation. Again, that is the variable that I'm trying to basically solve here. So that is just going to equal positive W now. Okay. And when we plug all of this into our calculator, what do we find? Well, we'll find that W is equal to 2163,91 newtons. That is the weight of our object. Okay, they could ask you for the mass of the object if they wanted to, in which case we use this formula here. We know that G is 9,8. So if they had to ask you for the mass, we know that that is W over G. We have W now, and we know G as it's the constant, and we can actually solve the mass of this object if we really wanted to. Okay, and that is, we'll leave it there for today. We've done 3 different examples, which is hopefully exposed you to all the kinds of resultant and vector type questions you might expect in an exam paper. And I hope this has helped. All the best, study hard. Mr. Moser out.